So I've given a couple of talks about this idea of how to run a multi-scale approximation to a hard problem. That hard problem is wave-driven sand transport. And I've argued in the past that what you have computed is the phase average quantities and statistics for the wave quantities. And those statistics are, root mean square wave height, free surface position, the mean free surface position. And that's not necessary. That's part of the problem for what's driving the sand transport. But you have underlying in that assumption is that you have something like a sinusoidal wave, and you don't have the nonlinear components like the undertow, the mass flux. So the whole idea behind the multi-scale approach was that we would capitalize on what we do well, that is the phase average problem, but we would add on to it, essentially invent the wave scale that lies underneath it. And so I've given a couple of talks on that, and a lot of those talks have been about the pyrotechnics of computing those wave-like quantities, given that you have the wave average quantities. And then we get to some point where we compare with data, and I had a set of rudimentary data that I was comparing with called BARTEX, which is good, but it's about 10 years old. And the results were okay. The gross transports were okay in their accuracy, but the net transports weren't very good. And the problem was, of course, difficulty in knowing how you went wrong. Did you go wrong with the depth dependence of the concentration profile, or the depth dependence of the velocity profile, or the bottom boundary condition? In other words, there's an endless list of things that you could have done wrong. We don't know which it is. We're going to try and sidestep a lot of that by using as much measured data, from a modern set of data, as much measured data as we can. I'll talk a little bit about the multi-scale and why I think it's important, and then I'm going to jump into the sediment transport part of it. And not to jump too far ahead here, but the disappointing part about what you're going to see today is that I'm going to come up with some results for the sediment concentration and sediment transport, because they get coupled together. And those results may seem reasonable to you and me and everyone else. The problem is that the data that was supposed to be available at this point is not available. And I don't mean to cast aspersions on that project, because what they're doing is mammoth, and it's really complicated. And I'll talk about that for a bit. So I understand why it's taking longer than they projected. That in itself is like a research topic, one that I'm not undertaking, but it's being undertaken at Oregon State. Let's see. Okay. So just by means of review, the sediment transport remains one of the largest, most complicated physics problems that we haven't been able to solve. Even with fine scale numerical models, we haven't done a very good job. We do an okay job with unidirectional flow, like river flow. Even that gets very complicated if you get things like ripples or sand waves. But we're from an engineering sense, we're making predictions that are on the order of a factor of 2 for river flow, concentration, and transport measurements. And a lot of that derives from more or less the Buckingham Pi theorem in a way, but that we relate the transport with U cubed. And so here I've written that the bed load is proportional to the dissipation due to friction, and that's equal to tau b times u, or U cubed is proportional to U cubed. And that's why it's sometimes referred to as a U cubed model, or an energetics model, or even a traction model. So that it doesn't really have it has a units-based fundamental sense to it, or background to it, and is originally due to Bagnall. And so that's commonly used, and it reached some level of success for unidirectional flow. But things get much, much more complicated when we add waves. First of all, it's not unidirectional anymore. You've got a time dependence. Here I've written that the overall suspended sediment in this expression here, and I think you can see my mouse, the expression here is equal to U times VS. And it's a good time to define this. VS could be thought of as a depth integrated concentration. So it's the total amount volumetrically of the concentration in the vertical profile. And that can then be separated because there's a wave component and a steady component to that. It can be, and they're uncorrelated. They can be separated out into the first term, which is the steady part, and then you have this complicated wave-like parts. That's the time average of the oscillatory parts. Now here, in contrast to the river flow, we don't have the luxury of assuming that we have got the total concentration as a function of the dissipation due to friction alone. For now, we need to account for some of the other complexities of the waves, like, for instance, the wave nonlinearity, where it'd be nice to just assume that U is sinusoidal, so the crest and the trough were the same. You could add it to a constant undertow or something like that, but you know what it's like, and you could. It's a tractable mathematics problem. But of course, if it's not, it may seem like a small thing that you've got, say, a Stokes wave that has a high peak and a low trough. It makes a big difference in the cross-shore sand transport problem. So you need to make some estimates of that. And in some of the other talks I've given on this, I talked about a lot of that complexity and the way it impacts the overall balance of sand transport. And so the other reason that it ends up being very complicated is you don't have just bottom boundary layer dissipation anymore. You also have breaking induced dissipation. So the idea there being that, you can expect that some of the dissipation that's going on near the bed does work and suspends sand from near the bed. There's also surface breaking dissipation quantity that makes its way to the bed. So some of that breaking induced dissipation actually also acts to suspend sand. And so we need to make some allowance for that. And the way we're doing it is more or less intuitive. And I've expressed it before, but I'll review it here today again. So what we end up with is a concentration profile that's not a linear function of the velocity, the square, the cube. And those are owing to a lot of the nonlinearities in the whole problem. Like, for instance, you've got non-zero sediment movement initiation by the Shields parameter. And then you've got phase lags. So that sand that gets suspended near the bed takes a little bit of time to make its way up into the water column, where incidentally the velocities, the wave orbital velocities, are larger because it's got a thin boundary layer. So that phase lag in velocity profiles and sediment concentration profiles makes this cross-shore sediment transport problem very difficult, and one that doesn't lend itself to just a simple algebraic explanation. And then of course you have, before we were saying that the sand transport is just a function of UQ. It's nice, right? But now we've got some kind of a vertical dependence to the sand transport in the suspended problem, especially when it comes to waves and that phase lag. So we need a way to making an estimate of all of that. So in a step towards a reasonable estimation of that, we're going to try and use these multi-phase wave models. One that computes what the wave-like motions are, the phase resolved motions, and then of course we do a reasonably good job already of doing the phase average ones, the mean ones. And so I think I mentioned this before, but previous talks that I've given on this spent a lot of time talking about how I'm going to make up the wave part of this. So I do spend a lot of time talking about the empirical procedures we use and the dependence on the Ursel parameter, and then a lot of data connected with measurements we have after we make laboratory measurements and show that works reasonably well. But of course, there's a whole host of things that you're still making up. You're making up all the bottom boundary layer problem. You're making up a lot of what the wave orbital velocity is compared based on the free surface position itself. And so You end up with a result that's maybe satisfying enough, but not as good as you want. You don't know where it went wrong. So here's what we're going to do today. We're going to try and make use of this high quality laboratory data that has this free surface and a velocity to drive this wave resolve model. And the phase resolve model too. We're going to use everything we can that's being measured as a way of sidestepping the errors that are induced in the previous part of that. Okay, so here's the main idea of this multi-scale modeling strategy. We're going to implement this multi-scale approach where we model the waves in a way that's as justifiable as we can. We either invent it with a synthetic time series like we've done in the past, or we're going to use measured data. So those are the 1 and 2 there. We can deploy a phased average model like a Batchelson-Janssen model, get all the wave average statistics. We can look at things like the Ursel number and figure out what a nonlinear profile works for, and then invent the free surface time series velocity. Or we can use the available measured data. Now, unfortunately, we don't have as much data as we eventually will. So I spent a lot of time trying to get my feet on the ground here with what was available to me, and that's, I have a small percentage of what I eventually will have available to me at this point. But most of what I have that's been quality checked is the free surface position. So a lot of what I'm going to be showing depends on the free surface time series. Okay, and then so we either invent it or we use measured data. This time we're using measured data as a way of trying to avoid some of the error that's induced in the invention process. And then we can numerically involve the relevant physics. In this case, of the sediment concentration and the sediment transport are the things that we're trying to solve. And we're solving it in a phase resolved way. And then if we have this available to us numerically solved in a phase resolved way, we can very simply numerically compute the time average. And then jump back to what we were starting with, which was the phased average model. So we could incorporate the things like the sediment transport back into the phased average. So that's the overall scheme of things that we're trying to accomplish. And so this is just an example of when we were inventing data. And this is a success story, by the way, of a prediction of wave height. And we don't want just wave height, right? We want to also know what the details of the phase resolved time series are. So this is a free stream velocity near the bed that's been measured and then predicted. And the data is shown as blue lines, and my predictions are shown here as black lines. And so you can see what we have, first of all, is a reasonably well predicted wave height overall. This is for 3 test cases, 5, 7, and 9 seconds. So low, medium, and high frequencies. And you can see that, of course, I've got the period right. It's a monochromatic wave, and we've introduced that as one of the boundary conditions. And then for the most part, we're doing a reasonably good at the extrema. The crest velocities and the trough velocities are both being reasonably well predicted, as demonstrated here on the right, where you have a 1-to-1 plot. Perfect agreement in the crest and in the trough would fall on the 1-to-1 line, the solid black line. 20% error shown in the dashed black lines. We do a pretty good job at this, and so I like to show this one. What we don't do quite as good a job at. Well, we do a reasonably good job then at evolving the sediment transport, although that model has changed a little, so I didn't show it here today. What we don't do as good a job with is the time averaged. So that's not the gross, but the net sediment transport. If we don't do just the forward motion and the backward motion of the sand transport, but we do the overall average, first of all, it's an order of magnitude smaller than the crest transport and the trough transport, but the data doesn't compare very well to the model results. And I argued at the time, still do, that one of the reasons is because we're not doing a very good job at some of the time average statistics, like the undertow. So I said what we need to do is really back off and use better represented phase average and phase resolve results. So that's how we started in on this sediment transport problem. So I don't have a whole lot of time to go into it, but I'm going to talk about it very quickly because the sand transport model is, of course, what we're after in the end. And this is an old slide, so I hope some of you can remember it. Remember that the volume of sand that's in suspension is just the overall depth integral of the volumetric concentration of sand. So that's the overall depth integrated. That's the total amount of sand in the water column. So it has units length because the concentration is volumetric concentration without units at all. And then, of course, you can figure out what your transport is by multiplying Vs times U, provided U doesn't have a great deal of structure. Now, all of this is open, to debate. Everything that I'm going to talk about is open to debate, especially when it comes to sediment transport, because as I've mentioned before, there's no end to the complexity that you can add to a sediment transport model. The idea here is to make it as simple as we can, such that we get some of the fundamentals done right, but avoids the intractability that would come about from an actual physics-based or F equals ma model, because they're simply out of reach computationally. The other thing that I've done is I've prescribed what the vertical variation of the suspended sediment transport profile is. And that's shown here as the exponential profile with a fall velocity and a mixing coefficient, a mixing viscosity, a turbulent mixing viscosity, and it goes like Z. So by doing this, I've said before, this is not right? It's bad. The question isn't whether it's bad. The question is whether it's pathologically bad. I mean, does it meet muster in terms of getting the fundamentals done well enough that we can make this problem that's essentially two-dimensional in this paper, two-dimensional, one-dimensional by dictating what the vertical profile is. And then, of course, I've shown in the right here a function that is a source where sand gets entrained from the bed as a pickup function and a fallout function F. So we're going to do a balance on this, but before that, I'll talk a little bit about the bed load layer. It's simpler. It's more akin to the river flow problem for a couple of reasons. One, we can use a U cubed model. It's commonly done. So it's Meyer, Pierre, Muller sort of model. And if you can forget about all the beginning of this is a shear stress less a critical shear stress. So if you've got a very large shear stress that goes like U squared relative to the critical shear stress, which is the Shield's initiation parameter, towards the 3/2, you can see you've got U squared times 3/2. So there you can recognize that we're getting back to something that's similar to a U cubed model. It's U cubed in the excess of the critical velocity, but it's still fundamentally, and in most cases, you have shear stresses in the surf zone that are much in excess of the critical shears. So it's close to a U cubed model. But one of the nice things about this is that while these are sometimes used as a phased average model, they're used in this case as a phase resolve model, because we have what the wave orbital velocities are at any point. Either we make it up or we measure it in this case. And then we can include things like the bottom slope, which is shown here as a GS. And so in my last TD, I covered this in some serious detail about how you get, even for a case where you have zero mean velocity. And so if you applied this equation to a model that had zero mean velocity, you can get sand transport in one. If you use it in a phase resolved way, you can get sand transport in one direction or the other if you use wave nonlinearity, or if you're applying it on a slope. And that really should be. It's just that it's too simple to use phased averaged quantities on this what should be phased resolved model. And so in this small little example here, I've got upslope. So with slope, you end up with transport that's larger in the down slope portion of this phase relative to the upslope. So if there's a wave going up and down a slope, you could imagine that what you would expect is to see more sand transport down slope than upslope. So whereas a phase average model wouldn't show this, we now have the opportunity to show that in a process-based way, which is nice. Okay, so remember our definition sketch, and this is the evolution. It's a conservation of sand equation. So this is sort of the fundamental evolution equation for the volume of suspended sand. So you can even forget about the advective acceleration, the advective term here. It's there because it should be, a physics-based way it should be, but it really doesn't fundamentally change too much of the number crunching I found in the end. It's there, but you don't have to think about it right now. What I'm saying is that the amount of sand in suspension, or the concentration integrated over depth, is equal to, it changes with time by pickup, making it larger, or fallout, which makes it smaller. It's easy to express the fallout. That's equal to some near bed concentration times the fall velocity. That one's actually relatively simple. We don't have exactly what the near bed concentration is unless we use the prescribed vertical profile that I introduced in 2 slides ago, which incidentally is a vertical balance of upward turbulent diffusion and downward fall velocity. Again, all up for debate, but it is a closure to this problem. So then you get a relatively simple expression for what the near bed velocity is. The near bed concentration. If you got the near bed concentration, you know what the fall velocity is. That's something that's provided by the user, and you can figure out how much sand is coming out. The pickup is cast in a similar sort of way, and it's cast in such a way that it has the correct units, of course, and that if you ran it until it was steady state, it would have the correct pickup function, meaning that it would match what's falling out. If you're running sand over a bed that's not moving in position with time, there's sand that's falling out all the time, but there's sand that's being picked up all the time too, that's in balance with it. So using that idea such that it has the correct time steady asymptote, you can get the expression for the pickup. It's dependent on an equilibrium value for what the sand concentration is, the total sand concentration. And that's shown here in this final boxed equation. It's a fairly important idea in the overall scheme of things here, in the sense that it says that you have amount of sand that's up in suspension that's due to 2 factors. And this isn't a first principle idea, but it doesn't violate any intuition. So it's not too different than Bagnall's ideas. And it is the basis for the entire seashore family. But it states that you've got a volume of suspended sand in equilibrium that's equal to the amount, the instantaneous dissipation due to breaking and the instantaneous dissipation due to friction. So that's where it's similar to the Bagnall model. But they're modified by some efficiencies. And these efficiencies are small numbers. They're like 1% or 0.5%. Because the energy dissipation that's going on is mostly being changed into heat, right? But there's a tiny little bit of it. It's not being changed into heat. It's going into suspending the sand off the bed and into the water column. So that's why those numbers, those efficiencies, are 1% or less. Okay, now it would be, you recognize that what I need is dissipation values that are not time steady but time dependent, right? You recall the expression for the pickup is due to the equilibrium value of the volume of suspended sand, and those are equal to the instantaneous values of the dissipation due to friction and dissipation due to breaking. Now, the frictional dissipation is straightforward. I mean, that's straight out of your undergrad fluid mechanics. You have a shear times U, or it's just a U cubed model, back to that. So we feel fairly confident about that part of it. We have no analogous accepted model for the breaking part of it. So there's surface dissipation, that's breaking. It's making its way to the bed if you have shallow enough water. And that dissipation near the bed, turbulent dissipation near the bed, is acting to suspend some sand. And so what we need to know is how that varies with a wave, right? We may know how it varies in a phase averaged way across the surf zone, because a lot of work has gone into that, and we've reached some level of maturity in those models. But we don't have it in a phase resolved way. So we adopted a more or less intuition-based dissipation equation that says that you've got dissipation that goes on as a pulse. And that dissipation goes on as a pulse when you have eta that's greater than eta 0. So that in this case, it's 0. And you have a forward, and d eta dt is more than 1. And that's equal to some proportionality constant and your dissipation due to breaking that comes out of your phase resolved model. In other words, what I'm saying is I know that over the phase of the wave, over the entirety of the wave, you've got a certain dissipation. But then I want to distribute it over the phasing of the wave. And so where we start with the red line, say 0.1 is our dissipation, we split that up into the phase resolved world where it has the same area under the graph, but it has 0 dissipation until it has a rising front face that's above 0. And then you end up with a pulse of dissipation. But it's a guess, right? We guessed based on that. And then of course you tailor alpha such that the area under the dashed line is the same as the area under the red line. We don't have any justification for such a thing, though. And so now this is where I start using the data that's available to me. And not all the data that I was hoping to have is available to me, but I'll at least provide what I can at this point. As part of the SED collab, the USERP SED collab experiments that took place not last summer, but the summer before. It starts and then finished last summer. The University of Washington and Oregon State Sediment Collaborative Experiment, laboratory experiment called STONE, sent wave packets down a sandy beach, and then they repeated these wave packets 15 times and looked at and they actually measured what the sand transport was under with sonic instrumentation, which is one of the advances we have here. They are at this time doing smooth particle hydrodynamics models of the entirety of that tank, which will be nice for me because I'm using a much lower fidelity hydrodynamic model, but these are not available yet. With the SPH model, they'll have essentially a digital twin of the whole experiment. So when I say, for instance, at this position, at this time, I want TKE, they'll be able to hand that to me, which is going to be nice for me. So then they had a more or less conventional data collection for part of it. They knew what the free surface position was with surface piercing wave gauges and a LiDAR. They had a hard bottom here through most of it, through a plywood bed with a slope. And then they went over a sand pit, and these red instruments are where they would actually measure not just, these are sonic instruments, so it's really super nice because they can shoot not just a certain position like an OBS might, but rather a line of positions based on time of flight and the echo distances. It's not at all simple though, in order to get these sediment transport. To get these sediment transport values, you get a backscatter amount that's proportional in some magical way to the amount of sediment concentration that you have, as long as you know the distribution of the sizes reasonably well. The time of flight tells you where you are. When you get a hard return, it tells you where the bottom was. So from a perspective of a modeler who's checking their models versus data, this is great. I'm really, really looking forward to getting this data. But Dr. Wilson at Oregon State has pointed out to me several times that it's going to be delayed, and it's because the task is monumental to get these things within an order of factor of 2. So the long and the short of it is I'm going to come up with concentrations, but I unfortunately don't have any data to really compare them with. So here's an example of the chirps that they would send. They would send wave packets down such that these wave packets were designed with a certain frequency distribution that they would break right over the sand pit, and they would dissipate their energy. So 15 in a row, I take and I stack these up one on top of each other. This is an example of 15 stacks one on top of each other, shown as a gray line. And then you can ensemble average these things. And we're going to want to ensemble average them, or they are in particular, because they're going to want to pick out things like what's the variation from the ensemble average as a way of determining what the TKE is. I'm not doing that, but I am using the ensemble averages that I've made up for the analysis here today. What we want to know is dissipation, and we don't want to know it in a time average sense. We want to know it in a phase resolve sense. So in a way to do that, we have to back up and look at the fundamental equations for the energy balance at any particular point. Here you have the energy density changing in time with the flux of energy into and out of a control volume equal by the dissipation. Of course, this is mechanical energy, right? Because if I was including the thermodynamic terms in the density and in the transport, then I'd have zero on the right-hand side. So everything that gets moved from something we can measure, so steady or wave orbital velocity or even TKE, is something that's measured. Everything else gets moved to heat, and that is counted as dissipation on the right-hand side. That's where that all goes. The mechanical energy dissipation density at a per unit area is a potential part and then a kinetic part. I've separated out, subtracted out the still water part, because I don't care how much potential energy I have at a particular place in the wave flume. What I care about is how much potential energy and kinetic energy I have when a wave is present, right? So I can just separate out and subtract off the resting state energy. And then you have the energy flux into and out of a control volume that's equal to a pressure part, a potential part, and then a kinetic part. And we don't have all of these measurements, right? We don't have, for instance, what pressure is at every particular location. So we end up using linear theory in this case, because that's a complete description of the kinematics. So whether or not it's right, I don't know, but it is a description that we can, we can handle. We're going to only go up to order Ka in the approximation here, so we're gonna look at whether or not we need to keep these kinetic energy parts. We've measured them, or we can compute them. We can compute them, and they're third order in Ka because you've got U cubed here, and so those can be tossed straight away. It's interesting though, I didn't toss them, right? Because I've always wondered about why that would ever be, or whether they really would be. And so here's a plot of the chirp that goes by, ensemble average chirp, by the way, where we have to use linear theory for the pressure and the velocities given our measured U, because free surface eta, because that's the singular value that we have that we trust at this point. And we get the energy flux as a function of eta. And we can look at the energy flux as a potential part. That's the blue part. So here's the peak of the packet that goes by. And then there's the kinetic part, which is both positive and negative, into and out of the water column. The potential part's just positive. And you can see that even based on these measurements alone, that it's justifiable to throw out the kinetic part and only keep things up to the order of Ka rather than Ka squared. Ka squared, not Ka cubed, excuse me. So we have an expression there for our energy flux. So let's now return to the overall energy balance. Remember that the end goal here is to get what the dissipation is, then in a phase resolved way. I want to know where in this wave packet dissipation occurs, because that's how I'm going to suspend sand in a time-dependent way. And we have to return to the overall energy balance, and then in a simple math operation. We can integrate over the entirety of the wave packet from the beginning, before the packet comes, and to the end after the packet is passed. And the nice part about that then is that the energy density before and after are zero. They're identically zero. So we lose the first two terms in the energy balance due to the energy density. And then we get an expression that says the change in the overall energy flux, and by overall, I mean integrated over time, is equal to the overall integration of dissipation. And since we have an expression for the energy flux, then we can find out what the time integrated energy dissipation is. Now, I know you're going to say, well, I really want the phase resolved, and we're going to get back to that. But it's a good start to get what the overall energy dissipation is. We can't use linear theory yet, right? You can't use E times C times N, which is the expression that you use for the energy flux in a linear wave, because what I have is a wave packet. I don't have a monochromatic waves train here. And if you look at that, the overall energy flux is equal to the energy dissipation before, and on the level section here, before it starts to break, you get what thankfully looks like a constant line, right? The energy is being conserved in the wave packet. It's undergoing transformations, right? Because it's shoaling and it's frequency shifting. They're moving at different speeds. The frequencies are moving at different speeds, but it's overall conserving energy. But then once it starts to break, you can see that it falls off precipitously. There's a little bit of noise in it, right? So I'm not going to take the overall numerical derivative, which is what I want. This ddx is what I'm after here to find out what the overall energy dissipation is. But I take an overall least squares fit after it begins and reaches its break point. And you end up with something that's like 70 kilograms per second squared, which matches up with those data reasonably well. So what we know now is, based on that slope, we know what the overall energy dissipation is integrated over time in the energy pack. But of course, what we want is the phase resolved energy dissipation. So what we have, we know we have the overall energy dissipation, but we have to return to the time-dependent world. And so what we're going to do, we're going to use the simplest phase resolving form that we can in order to get a sense of it. We're not going to do too badly in its overall, because we know what the overall integrated wave dissipation is for that wave packet. But we don't know how to distribute it through the time series. So we're going to return to the phase resolved world. And this is just, this is again the energy density and the horizontal gradient of the energy flux, where we're using the expressions for shallow water, for progressive shallow water waves in positive x. Now, we could just start to populate this equation, right? The first one's easy enough. We know what eta is, and we know what it is every 0.02 seconds, right? We measured it at 50 hertz. So that one's easy. What we don't have is the spatial part. So we don't have the gradients in the energy flux that are required for the second term. And we don't have it. We have a series of wave gauges. But think about, we're looking at this thing that's happening every 2 seconds. This wave's happening every 2 seconds. And our gauge spacing is something like a meter apart. So we're not going to be able to take spatial gradients based on a meter apart with a wavelength that's 5 meters or something. So we ended up having to do some pyrotechnics on that and casting the free surface as some kind of an amplitude function A, and then a shape function F, where F is assumed to be the shape that moves without change in form. So this is saying that, okay, you might have a wave here that has a certain shape F, and the wave after it breaks is also of the same shape F, but with a smaller amplitude. So this A is a decaying amplitude for saturated breakers, and F is whatever the central gauge ends up being. And then we use, and this is a bad graphic for this. I'm not sure why this one ever made it in here, because this doesn't do it justice, but you can compute what the spatial distribution of A is. That's the amplitude. You could also say something like it's saturated, but that's not that's not a good estimate in many cases at the initiation of braking. So we chose to numerically estimate what the dissipation or the spatial distribution of A was based on triplets of wave gauges. And then you can generate. So you've got a form for the free surface position that's sort of written in a general way, and you can make then synthetic time series that are right to the right of the wave gauge and right to the left of the gauge. And they won't be separated, of course, by 1 meter. We'd be using measured data, but they're going to be separated by c times delta t, where delta t is 0.02 seconds. That's the phasing, the dt of the time series collection. So what you end up with is an expression for the free surface that's directly behind it and directly before it, that's invented from the centrally located wave gauge and the decay in the wave height based on neighboring wave gauges. I hope I'm making that clear. So here's a quick expression. Here, this is again a triplet of wave gauges, where the red is the first gauge, wave gauge 3, and wave gauge 2 is in the center, and wave gauge 1, shown in black, is the the trailing gauge. So this is a quick demonstration of how, if we use constant form, that means that A has no value, or it should be 1. Sorry there. Oh, but AX is equal to 0, right? There's no gradient in AX. And then we can use the linear phase speed associated with the fundamental frequency of the wave packet, 2.5 seconds. And we end up with eta plus and eta minus shift in time by that small delta t. And you can see how even using a linear wave speed, we end up with wave shapes that are before and after the central wave gauge that are pretty well represented. Anyway, all of this is a way of getting the spatial distributions of the wave gauge. So now we have a synthetic distribution of the free surface time series at even small separation distances, and we can resolve the dissipation D based on the energy equation. And we end up with something where the free surface is shown here as a blue line, and the dissipation is scaled here but it's shown as a red line. And you can see that, for one thing, it's almost symmetric with it's almost a 1-to-1 with the free surface position itself, except that for small departures from the free surface position, you end up with, well, it's not a 1-to-1. It's not proportional. What you're going to find is that it's much more likely to be a square. Now, of course, we have data here. And so we can do this all day long without recognizing whether or not it's right in its more fundamental way. We have these data, but we're working towards a more general model where we actually want to know, based on a situation where we don't have data, where the wave dissipation occurs in the phase of the wave. So we can generalize this phasing of the distribution by substituting those assumed forms for eta and velocity and pressure. And you end up with something that looks like dissipation goes like eta squared, proportional to eta squared. Not exactly, right? Because there's other, like I've assumed that the phase velocity is a function of position, of course it is. But in a sense, it can be expressed as a function of eta squared with some degree of certainty. So it's approximately proportional to the square of the free surface position. And we can choose the beta, which is just a linear scalar parameter here. We could either compute it by its fitted amplitude A, or it can be selected to satisfy the overall computed total dissipation estimated energy equation, which is what I've done here. So this is one example of one test and one gauge where you look at the degree to which, in actuality, the dissipation is a function of eta squared. And so you can see it would fall exactly on a line if this were true. but they're all sort of reasonable. And so it's one of these maybe far-reaching assumptions you end up having to take in order to get practical results from a difficult problem. And so this is an example from wave gauge 7, which is inside the breaking and the mid-surf, where we have a measured free surface position, and then the dissipation due to breaking is shown here as the dashed red line, which looks, by the way, fundamentally different than the one that we initially guessed at, which was that you have a dissipation that only occurs on the rising front of the waves. It's not the way that the math rolls out at all here, right? It looks symmetric front and back. It only depends on eta squared. Okay, so when we have what the phasing of the sediment, the dissipation is, we have suitably accurate dissipation due to breaking, dissipation due to friction. We can compute what the volume of suspended sediment is. And that's what we're after in the end. We want to know what the volume of suspended sediment is, or the concentration distribution over the over the water column. And of course, that comes from the numerical integration of the evolution equation that I showed you earlier for the volume of suspended sediment, where we now have boundary conditions or equilibrium conditions that we have some justification for, because we know what the phasing of the dissipation in the bottom boundary layer is. So this is an expression that shows you what the total, that the equilibrium value is, which is shown as a dashed line, and what the actual computed value is. So the equilibrium value changes instantaneously with dissipation. And of course, it takes time to bring sand up and into the water column by the evolution equation, and so it's shown as the dashed red line. So in every case here, what you have is a lag of the near bed concentration relative to the equilibrium concentrations, which is exactly what you'd expect. I don't have time to talk about this. I can't believe I'm running out of time, but there's another whole aspect of this problem that goes into figuring out what the sediment diffusivity is. We've assumed that the sediment diffusivity is the same as the momentum diffusivity, which probably okay, right? I mean, there's people who argue that they're a little bit different, but I don't know. There's so much hand waving that goes on in these models that I can't imagine that it makes too much difference. Let's just make it short here to say that the sediment diffusivity derives from this linear superposition of three things: the waves, the bottom shear dissipation, and the breaking dissipation. So that sort of dictates how much water is going up into the, sand is going up and into the water column. Okay, so this is a result that you get if you at wave gauge 7, again in the mid-surf zone, where there's a computation of the volume of suspended sand, and you use the prescribed sediment concentration profile over depth. So here, this is with time, and it's sort of this wave gauge 7, and I've computed, this is kilograms per meter cubed, or grams per cc, and over depth. This is only over the first 5 centimeters. So you can see that, and this is as much as you expect. There's an exponential distribution of concentrations at the bed. It all happens near the bed, right? That's where the whole entirety of the game is. Now, this may appear to be reasonable, but unfortunately, we don't have the data to show whether or not this corresponds well to the measured data. And again, I'm not complaining about the delay in the data. I understand how difficult it is to come at that problem, the one that they're approaching. Okay. This is a quick background. The two-scale approximation is a way of including waves in a fundamentally justifiable way. So now we can include things like skewness or wave nonlinearity in the shape, including the nonlinearity of the orbital velocity and the current part of the problem. You can include the effect of the bed slope. And also you can include the phase lags that go on because it takes time to bring sand from the bottom and up into the water column. And I've covered that in greater detail in some previous technical discussions. Today we're talking about the requirement that I have coming across, that I need to know what dissipation is, and I need to know what it is in a phase resolved way. And it's not like they're going to be measuring that anyway. So this is an exercise that was of some value even when we get the data. We need to know what velocity is. We can measure that, but we need to know what the dissipation is due to braking and the dissipation is due to friction. So we're always going to need submodels for that anyway. This phase resolving data that we have are ideal data for populating these boundary conditions, especially when we get the velocity. And I don't rely on the free surface position in order to figure out what the velocities are. So these are a complete set of results, and they don't violate any deep-seated belief that I have. But of course, it could be anything, right? I could be off by 2 orders of magnitude here, and it would still, everyone might still politely nod their heads where I could be dead wrong. And so a comparison to actual sediment data is absolutely necessary. March is a possible date for this. I'm looking forward to getting those data as soon as I can. And I know they're working hard on them. So, all right, I don't know how, Marissa. I'm sorry. I'm left on with only 3 minutes.